Hi, in this video, we want to continue talking about k-means clustering. And we want to talk about, hey, is this a good cluster? Is this a bad cluster? Do we want to keep it? Do we want to throw it away? So what we want to do, we want to look at some diagnostics on ways to decide, do we have a good clustering? Okay, so first thing we're going to do, we're going to load our data. Scrolling down, I'm using R Markdown. Now, I'm going to use the same data set from the previous video. I'm going to use this decathlon data from the ClustovArs package. And then I'm going to, here I go ahead and I order, I sort the data by the number of points that the athlete got. That way, intuitively, when I'm looking through my output, I can see that the stronger athletes should be at the bottom, the ones that are more competitive, and the ones that are less competitive will be at the top. And what I'm going to do here in this step, I'm defining all the columns I want to use. So I'm going keep vector of the column names that we want to keep. And then I'm reducing my data set only to the measurements I want. That way I'm not polluting anything. I can just grab it. Then remember, whenever I do clustering, I should strongly consider rescaling my data in some way, shape, or form, either transforming the range to 0, 1 or normalizing it. I like to normalize because of my statistics background. So that's what I'm going to choose to do. I'm going to take the scale function from each column here in this data set. It's going to subtract the sample average and divide by the sample standard deviation. So in the scaled version of M, all the columns have average 0 and standard deviation 1. So everything's standardized. If I don't do that, what's going to end up happening is that the 1500 meter, because it's so much bigger of observations, when I do the algorithm, it's going to try and minimize the distance between points. It's really going to look at the 1500 almost exclusively. And if I wanted to do that, I just would only have one column. Now, remember my convention that I personally use is I use a function and then what its input is whenever I create an R object. I find that's a good way to remember things. The other thing I do is if I have a vector or a list or a data matrix, I'll put a list or a capital M. Like here, I've got just a capital M for my data matrix. All right, so one thing we want to consider, we can have different number of clusters. So how do we get different number of clusters? Well, what I can do, either I can give R these initial centers that I want to use, or I can give the number and then let R randomly pick. Now remember, I can have problems with reproducibility down the road. So if I get a result I really like, but I didn't set the centers, then when I compute it, I probably won't get the result I want. You can set seed to kind of avoid that, but the best way is to give the initial centers if you can. All right, and so there's going to be 2 centers. Here's the first one, the average of each of the rescaled values for each of the events in the first cluster is up here. And because of issues with just not having enough space to print, discus is down here. So we can see that, remember 0 is average. So this group, they're stronger on the running, but overall they're weaker on the other events. So this group is good at sprinting, good at pole vault, but weak on the other jumps, and weaker at javelin, weaker at discus. This group, we've got negatives, so they are weaker at sprinting, slightly weaker at pole vault, and then they're strong at the jump, strong at the javelin, strong at the discus. All right, so here we can see that. So I would bet, I don't know much about pole vault, honestly, but it looks like if you want to be a good pole vaulter, you're going to have some good speed. Well, with these events, I'm going to go ahead and make a guess that, the javelin definitely is going to require some explosive leg strength right before you throw it. discus, you're gonna have a lot of like hip strength, like very explosive hip strength. And so that's gonna be the same on the jumps. So it's kind of interesting that it's grouping by like which part of the body is most important in these events. Okay, so now let's scroll down and see what, and the output gives us for each individual which group they're in. Okay, that's interesting. Now, I want us to pay attention to this. Here we've got the between sum of squares divided by the total sum of squares. And we can see that it's just under 20%. All right, remember, total sum of squares is equal to the between sum of squares divided by the within sum of squares. So if I had the greatest clustering possible, what I would have very few clusterings, and the between sum of squares would be very large proportionately to the total sum of squares. It will always be less, like this will always be less than 100%. But if this is close to 100%, I can be more confident that I have a good clustering. But there's a catch. If I go and I did clustering on all the points, it's going to automatically be 100%. All right, so that would not be a useful clustering because we never grouped them together. Okay, so what we're going to do in a moment, we're going to try and look, how can I get the most between sum of squares for the least number of clusters possible? That's what we actually want. I want the most between sum of squares for the least number of clusters. Okay, now, remember, I told you sum of squares total is equal to sum of squares between plus sum of squares within. Maximizing between sum of squares is the same as minimizing within sum of squares. Okay, so trying to maximize this one is equivalent to trying to minimize the within sum of squares. In a moment, we're going to look at some plots that focus on the within sum of squares rather than the between sum of squares. All right, so now let's go down. Got some interesting groups. Let's see what we got. All right, so this group got negatives on sprints, and oh, this time high jump is sticking out. Kind of interesting. Now here we had 3 groups, and so what's going to happen is this number will always go up as you increase the number of clusters within a few percentage points. Because of the whole randomness aspect, it might not actually go up, but in general, it's going to go up as you increase the number of clusters. So just because this is bigger doesn't mean this is a better clustering. We have to dig in and figure things out. All right, so something that you have to decide when you do k-means clustering is you have to decide how many clusters to use. Okay, so if I've got a project and I know the number to use, boom, I go with that. If I have some knowledge about the data that leads me to decide for something, I'm going to use that. In this situation, we're going to assume we don't know. We have no idea. We want to check it out. Okay, so what I'm going to do, I'm going to build up the k-means clustering that we did in the previous video. Remember where I broke it into 4 different groups where we've got strong overall, weak overall, strong on the running, weak on the field events, and then weak on the running, strong on the field events. So we have 4 different groups, and we build the initial centers this way. And we can see, like I put the row names on here so we can see it's easier to interpret what's going on. So remember, negative on the runs is good, positive on the field events is good. So I actually misspoke a few minutes ago. Pretend I didn't. I got the numbers kind of mixed up when I start looking at the 2 cluster k-means. Please forgive me. All right, so I go ahead and I just build it, and we go ahead and take a look at the output. And if you remember from the previous video, it's exactly what we intended it to be. and we're looking at 37.5% now. Is that good? I don't know. It depends on what the other cluster sizes would give us. So it's, you know, good or bad is relative to the rest. All right, so first thing I want to do when I want to diagnose a k-means clustering is I want to make a scatter plot using principal components. We did this in the previous video. I did it manually with ggplot. I prefer the manual way. Here, we're going to use it. We're going to do the lazy way. We're going to let some functions take care of it and generate it for us quickly. If you want to make things a little bit more interesting, more juicy, you're going to have to dig in and do it manually. But these are very good ways to go. All right, so the useful package gives me a function. So remember, in R, I've got the package. I have double colon, then the function I need. All right, I've got two choices when I use a function within a package. Either I can load the entire package, or the second option is to pull out just the function I need. If I load the entire package, what will happen is I can have different packages that can have the same name for different functions. And if that happens, then what can potentially happen is you get package confusion. R is just going to grab one. It's going to grab the most recently loaded one that may or not be the one that you actually want when you're running your code. So I try not to load packages as much as possible. So here, I'm pulling out just the function I need, and that's the only thing I'm using. There are times in R where you have to load the entire package. There I use the library function. We'll talk about that later when that comes up. All right, so now let's actually take a look. All right, so I can see that my first group is on the far left. My second group is on the far right. So remember, these are the weaker overall, stronger overall. The third ones are, let's see, what was 3? I can't remember. Okay, strong run, weak throw. So strong run, weak throw. And that is group 4. There we go. Put back down. Okay, so the first principal component says, hey, how good are they overall? The second principal component is looking at them on a spectrum of being a runner to a fields event person. It kind of gives us like a continuum of value, so we can say, are they, you know, overall, like this person right here, they're going to be very balanced. This person is very balanced. They suck, but they're balanced. This person's very competitive, and he's balanced overall. While this person over here is strong in one category and weak in the other, this person is strong in the opposite category and weak in the opposite. Okay. Now, there's a whole bunch of functions in R to do this. Basically, just pick the one that you feel looks the nicest. So this one is inside the, what is it, useful? Yeah, the useful package. It's kind of a rare package to come across, but it does it so nicely and easily, I couldn't resist. Now here we're using the cluster package cluster plot. And it's not very pretty, but it's nice that it gives the names on there very easily. And it says it can, explains about 50% of the point variability. Nice to know. Now the FPC package has a bunch of cluster functions to help us out. What we have to do, we have to enter our data and we have to enter the index of clustering. Let's see what that looks like. All right, so it just gives a number and it plots it. Same plot that we had previously. And you just have to use the one that you feel like it looks the best. This one looks a lot better on a screen where you can maximize it. It's not so crowded. And it's nice that it gives the multivariate normal ellipses plots for us. that'll be useful down the road when we talk about model-based clustering. Now, next one is the fviz cluster. So here we pass it the k-means object and the data. If I, I'll say that in a moment. Let's take a look. So it goes ahead and uses ggplot once again, and it plots it, and then it does a non-regular polygon around our data to encompass it and help us see what's going on. Now, the clustplot one gave us the multivariate normal ellipses, which we might be interested in. The polygons are definitely going to be useful regardless of our assumed distribution. And it's nice that it gives different colors, gives different points, shapes, and it labels everything. So that's kind of nice. So what am I looking for when I look at this? If I see that these like clouds of points are overlapping with each other, or different clusters have overlapping points, that makes me less confident. Now, remember, I'm doing higher dimension statistics. In higher dimensions, you're going to have a little bit of overlap. You see that I've got a red point and a blue point kind of like going into each other's territory. Well, that's because, remember, I've got like 10 different events going on. If I had this in higher dimensions, these clouds of points are not really overlapping like that, probably at all, honestly, on this plot. And so if I could visualize 10 dimensions and look at this, I could see how they're better separated. Here, we're taking 10-dimensional data space and compressing it down to 2. There's going to be some information loss. You got to deal with it. Okay, so now here, let's take a look. Or so if this plot, we use it to see, do I have good clustering after I have a given number of clusters to run? So if I could change the number and rerun these plots over and over. Next thing we're going to talk about is we're going to try and figure out, before I start looking at individual clusterings, what number should I pick? So what we're going to do, we're going to look at the elbow method, and we're going to be talking about sum of squares. Remember, sum of squares is sample variance without being divided. Okay, so let's move that. All right, we want as much of the sum of squares to be within the between sum of squares, and as little as possible to be within the within sum of squares. So sum of squares total is equal to sum of squares between and sum of squares within. And I want to have as few clusters as possible, because the fewer clusters I have, the more parsimonious my model is. All right, so now let's go ahead and let's use the fviz NB cluster packet function in the facto extra package. And I'm going, here's my data. Here's the method that I'm going to pick. And I'm going to be looking at the within sum of squares plot. All right, what this is going to do, this is going to go through a whole bunch of different values and for the number of clusters, and it's going to randomly pick those, or pick the clusters, initial centers, and then it's going to show me what is the within sum of squares for each of those. So if I want to make this reproducible, I'm going to go with set seed. And 823 is UCF on a telephone. All right, so I can see that it keeps on going down, which is what I expect. What I'm looking for is, where do I get diminishing returns? Where do I have to go? If I increase, do I get less than I did before? Okay, so here there's a big drop here, and then there's not much of a drop. So maybe a 1 or a 2, well, maybe like a 2 here. So what we're kind of looking for, you see how it kind of bends? It's kind of like an elbow to it. And down here, there's another elbow. And we see that there's another bend. And so because of this bend, and it's kind of flattening out to the right, goes down, then it's less steep. We call it an elbow. 2 looks kind of interesting to me. but 4 also does too. We can see that it kind of, there's not really much bend after that. So 4 is definitely one I would want to consider also. Oh, something I need to say about this. When you start doing this, you are going to get different measurements are going to say different number of clusters. That's going to happen. You have to kind of look at the whole composite information, take a gestalt, and decide from that. All right, now, another way we can look at it is silhouette computations. We're not going to go into the actual computations of silhouettes here. We will do that later when we look at hierarchical clustering and other methods. So what silhouette calculations do, they look at individual points and ask the question, does this point belong in its cluster? If I get a big value, I'm very confident that that point belongs in its cluster. If I get a small value, I'm less confident. That's basically how it works. And so what will end up happening is that points that are close to the center of their cluster will have very large values, and then the points that are on the periphery are going to be the ones where it's like, I'm not so sure, maybe, maybe not. I promise you, you're going to have some, no matter how you do your clustering, you're going to have points that look like they don't belong. Ultimately, you have to look at the whole package. So when I do this, I take the facto extra package, fviz mbclust, just like I did before, but this time my method is silhouette. What this is going to do, it's going to do the silhouette calculations I just described, and it's going to average them. And with the averaging, then I can kind of get a feel for overall what is best. Let's scroll down, let's take a look. All right, so here we can see that we get a good improvement going 1 to 2, and then it comes crashing down. All right, so off of this is looking like we should go with 2. All right, and kind of interesting that 4 is coming out low. Remember, this used a random number generator to choose the initial centers. If I ran this again, I will get a different plot. And that might mean, it might tell me that a different number of clusters is the right way to go. Now, for gap statistics, it looks at the intra-cluster variation. So the clusters, the variation between the cluster centers. And once again, we're looking for diminishing returns. So the cluster package has a whole bunch of tools to help us out when we are working with clustering. And the function is clustgap. I put in my data, I put in the clustering algorithm I want to use, and the maximum number of clusters I'm considering. I put in 40 because 41 is the number of data points I have, and 40 is the maximum number of clusters that we can have. Because if I have individual points, it doesn't make sense to be grouping. It gives me some output, and you'll notice that it does a bootstrap for us, which is nice. And so it gives us some statistics. It just kind of spits out a whole bunch of stuff when I print it. All right, so now let's go ahead and plot it. So I'm going to take the cluster gap statistics I just computed. So this is the object I computed with the previous code that we looked at. That gave us all that output. Wow, that's a lot. That's a lot of stuff to look at. Okay, so what I want to do, I want to look at the far left, focus on the far left. What I want to do, I want to find where do I have like a peak, and then it starts going downhill. So I want to cut off all of this. I really want to ignore all of this business and just look at this downward slope. All right, so when I look at this, this is saying like 1 is the best, which doesn't really make sense. And then we see that, is that 6 or 7, something like that. 1, 2, 3, 4, 5, 6. Okay, so this is concluding that 6 would be a good way to go. Remember, now this used a random number generator, so if I run this again, I'm going to get different results. And the plot looks much nicer on a screen than on our Markdown, by the way. Once again, the Facto Extra has some tools to help us out. And here I'm putting the method to gap stat. What this is going to do, this is going to just limit it down to 10, if I remember correctly by default. And this says that we just want one cluster, which is the entire data set, which is saying don't cluster at all. Remember, you will get contradictory information when you do clustering diagnostics. Now we want to take a look at the actual statistics. When you do this, I feel like you should really go in the order that I present this in. The most important one is that principal component plot. That one is the one you really want to go with. Now, when I look at cluster stats, this just kind of vomits out a bunch of information that I can look at. So I pass a distance function. So here I'm taking the Euclidean distance between the different rows of data. And then I'm taking the k-means clustering that we've got. And then this is going to compute a bunch of statistics for us. When I do k-means clustering, it's set up so that it uses a Euclidean distance. Therefore, when I do a distance here, I want to use Euclidean distance to compute it. Euclidean is the default one in R. It's all, in like every language, it's the default. So I don't have to specify. If I was using a different method that used like the 1 norm instead of the 2 norm, I would change the method in this distance command. All right, so our number of data points, number of clusters, cluster sizes, minimum cluster size. If I have a really big data set and I have a whole bunch of clusters, this might be hard to look at, hard to read. All right, so if I have good clustering, I should have a good number of points in every single cluster, intuitively. Now, it doesn't always work out that way. So if I end up having a really small minimum number of points in a clustering, then I might want to take a look, might want to get rid of that cluster altogether and go one down. Now the diameter is the distance from, basically the longest distance between 2 points in the same cluster. And we can see it's 5, 6, 6, 5. I want this to be small as possible. And here's the average distance. So here we take all n choose 2 points in a cluster. So I took the first and the second in a cluster, compute the distance. The first and the third, compute the distance. The second and the third, compute the distance. And then I keep on doing that, get all the pairs I can get going, and then I take the average. Here's the median distance. Remember, if I see a difference between a mean and median, I probably have skewed data. So check it out. Separation to measure out how far apart they're getting. I believe that is the distance between the closest points in different, no, that's wrong. I have to look up, I don't remember. That's in the help documentation, you can look it up. I'll give that to you as homework. Here's a separation matrix. So here, this tells me what is the distance between each cluster. Okay, this is the distance to the closest cluster to this one. So what it's doing is taking all the different points in one cluster and all the different points in a different cluster, and it computes the distances between them. And here, this is how close are the closest two between each cluster. And here's the smallest for each row. Here's the average distance between the different clusters. So we want this to be big, we want this to be big, we want this to be big. This tells me kind of like an overall average between, average within. Now here's the number between, when I start like going across different points, the number of within sum of squares, maximum diameter of all of my points. So here, if I have good clustering, they're going to be tight. If they're tight, the max diameter will be smaller. Okay, so that's something to consider. And now, as I go through, if I change the number of clusters I have, these values are going to change. And some of the values are going to go in the good direction. Some are going to go in the bad direction. And you have to judge a composite. Overall, minimum separation, I want this to be big. Here's my average silhouette width. Average silhouette, so this tells me overall what's going on. G2, we're not going to worry about too much. Pearson gamma, entropy, if you're interested in information theory. Now this is rounded off, so this isn't really being that informative. And cluster-wide gap, widest gap. So, you know, now there's just a lot to go through. And my opinion, the statistics way is not the way to go. The way is to go the visualizations, because we think with our eyes, and that'll work out pretty well. So that's all I've got. I hope you're doing well, and good night.